Let's discuss rational functions. Now there's one rational function you've probably seen before, and it looks something like this. Y equals 1 over x. And we used to call this the reciprocal function, actually. But it's also a simple case of a rational function. When I say rational, I just mean a fraction in a function, right? Something over something. A polynomial over another polynomial. And if we want to graph this, and this should be a review, set up your x and y axes like this. You're going to have two asymptotes, right? Because if you think about what x is allowed to be, right, x can be pretty much any number other than 0, because you can't divide by 0. So for that reason, x can't be 0, and you have a vertical asymptote here, right? Another way to say it would be that the function is not defined when x is equal to 0. So you can say vertical asymptote at x equals 0. Likewise, there's no value for x you could divide by that gives you a y value of 0, right? So y also cannot be 0. Meaning that the graph is not defined when y is 0, so you have a horizontal asymptote at y equals 0. Just like that. And then if you were to plug in some points for x, you would see that it makes a curve that goes like this on the right and like this on the left, right? Where you get closer and closer to those asymptotes, the further you go right and left or up or down. And then in the middle, you just kind of swing like that. You just have a little curve, okay? And then we learned how to do transformations with these, right? We said that if you have y equals 1 over x plus 1, well, if you add 1 to x, that means you move 1 to the left. And in the context of these rational functions, it makes sense because if you want to find the vertical asymptote, you're just figuring out where the bottom here, your denominator, is equal to 0. So you could say x plus 1 equals 0, solve for x equals -1, therefore that's where your vertical asymptote is. And so you could say, okay, -1, I have a vertical asymptote. The horizontal asymptote doesn't change, it's still here at 0. And then you draw your sketch like this. And of course, it appears that the graph has moved over 1 to the left, and it has, right? But when it comes to rational functions, we like to do it this way, where we say, oh, you set the bottom to 0, like this, solve for x, that's where the vertical asymptote is. Because when x is -1, that would make the bottom undefined. Or it would make the bottom 0 and the whole function undefined, I should say. So hopefully that makes sense. We also discussed how if you add a number to the end of the function, so something like y equals 1 over x plus 1, that moves the whole graph up 1, right? And you can think of that as a transformation, that's fine, right? So it's a vertical shift up 1, so your horizontal asymptote goes up to 1, like that. Your vertical asymptote is still here at 0, and you fill in your graph, it'll just look like this. And if you decide to do something where, you make the graph negative, like y equals -1 over x, that would be a vertical reflection, right? So instead of looking like this, you would have it flip downward, and it would look like this. All right, just like that. And if you decide to put the negative here on the x instead, and you say that's a horizontal reflection because it's on the x, well, if you were to reflect this horizontally versus vertically, it doesn't really make a difference. You end up getting the same shape. And that makes sense algebraically as well, because when you divide by a negative, that negative can just be moved to the top. So if any part of this is negative, it's going to reflect. Okay? Now that's y equals 1 over x. But you could also do other things, right? You could do y equals 1 over x squared. I don't believe we've looked at this one before, but that just looks something like this. You have the same restrictions, right? Y can't be 0 and x can't be 0, because if it is, then it's undefined. So you have the same asymptotes, but then when you go ahead and plug in some x and y values, you get a curve that looks like this on top, and a curve that looks like this. So normally it's this one on the right and then one down here, but instead the one on the bottom is actually on top. And the reason is, no matter what value of x you plug in, positive or negative, this whole thing is going to be positive. Because when you square a positive number, or if you square a negative number, they're both going to become positive, right? So you only get positive y values, so you only have curves up here in the positive y values section of your function, right? Those top two quadrants, okay? So hopefully that makes sense. You could also have y equals 1 over and then do something like x plus 1 squared. So that plus 1 is inside the function, so we're still moving 1 to the left, right? Same concept. And another way to think about that is you set the bottom to 0, solve for x, and that's where your vertical asymptote is, right? Same principle. And then you have your curve like that and like this. And you could also make these things negative, right? Like I could say y equals negative 1 over x squared, and that would just look like this. So the same as this one on the top, except they're upside down, right? It's been reflected vertically. So all those rules still apply. Now those were two types of reciprocal functions, and like I said at the beginning, those are technically a type of rational function, but in general, a rational function is just anything where you have p of x, where p is a polynomial, divided by q of x, where q is another polynomial, right? So we can look at some examples of what you could expect to see. So you could see something like f of x equals 4 over x squared plus 2, right? Not completely different to what we were just working with. But you could also have something like f of x equals x squared plus 1 over 4x squared plus 2x plus 1, so second degree over a second degree. But you could also have something like f of x equals x squared plus 3x plus 2 divided by 3x plus 1. So the degree on the bottom could be bigger, the degree on the top could be bigger, it could be the same. Like there's no restrictions as to what is allowed to happen here, although the shapes will look very different depending on what you have, and that's what we have to go through. So what I'm going to do next is give you some steps that we need in order to sketch these functions, okay? So first what we have to do is determine the horizontal asymptote, and some people will give you like these steps in different orders, and this is just how I like to do it. So to determine the horizontal asymptote, you gotta look at your function f of x, and usually if it's written in standard form, you're gonna have something like cx to the a plus a bunch of other terms divided by dx to the b plus a bunch of other terms, okay? So these are just generalizations, right? So c and d could be any numbers, a and b could be any numbers. But based on what these numbers are, the horizontal asymptote is going to change. And let me show you what I mean. If a is less than b, so if the exponent on the bottom is bigger than the exponent on top, what that means is that your horizontal asymptote is at y equals 0. And we saw that with some of the reciprocal functions, right? Like y equals 1 over x or y equals 1 over x squared. The exponent on the bottom was bigger, so we just assumed the horizontal asymptote was at y equals 0, right? So that's kind of what we're used to seeing. But there's also some other things that could happen. You could have a and b being the same number, right? So if a and b are both the same exponent, then what you have is a horizontal asymptote at the value y equals c over d, where c and d are those coefficients. So that's kind of an interesting case, right? Like if c is 2 and d is 1, and the exponents are both, those terms are both x squared, then your horizontal asymptote would be at y equals 2 over 1, or 2, right? So that relationship is going to make a big difference. And then you have this third case where a is bigger than b. And if a is bigger than b, then you don't have a horizontal asymptote at all. You just say there's no horizontal asymptote. So if the degree on top is bigger than the one on the bottom, you don't have a horizontal asymptote. Now, a special case of that is if a is bigger than b by only 1. So like if a is x cubed and on the bottom you have x squared, then this situation would come into play. And what happens here is that you have a slant, or you might hear the phrase oblique asymptote. If you have a slant or oblique asymptote, that's just an asymptote that goes on a diagonal line. So if the degree on top is bigger than the one on the bottom by exactly 1 unit, so if it's like x cubed over x squared, something like that, then you would have a slant or an oblique asymptote. So an asymptote that's going on a diagonal, and that's instead of a horizontal, right? So you'd probably have an oblique asymptote like this and a vertical one like that, as opposed to a vertical and a horizontal, okay? So with all that in mind, you should be able to figure out what the horizontal asymptote of your function is, okay? And we're going to do lots of examples of these, so don't worry. Now that's the first step, right? That was all just the first step, finding the horizontal asymptote. The second step, I would say, is to factor the top and bottom, or the numerator and the denominator, right? So just factor everything you can. And then what you want to do, so part of that step is you want to note if anything cancels. So once you factor everything, see if anything on the top and bottom cancel. If they do, that indicates that there is a hole. So if you have like a bracket on top that says x minus 2 and a bracket on the bottom that says x minus 2 and they cancel out, what that means is that you have a hole at x equals 2 at that location. So we'll do an example of that, don't worry. But for now, just know that's what it means. And then the other thing you want to do is set the denominator, the bottom of your fraction, to 0 and solve for x. And what that's going to do is tell you where your vertical asymptotes are, right? So now you should have your vertical asymptote, your horizontal asymptote, any holes you might have, which, isn't that common, but you might have some questions where there's a hole. And then finally, what I would do is find the x and y intercepts, which you should know how to do by now, right? It's the same process for every type of function. If you set x to 0, you can find the y-intercept. If you set y to 0, you can solve for x and get the x-intercept, right? That's all you have to do. So I would say make sure you do this, right, for sure, and that way you can graph a nice, accurate version of your function. So just to recap, we find the horizontal asymptote using this rule about the exponents. We factor the top and bottom. If anything cancels, that means there's a hole. You set the denominator to 0 and solve for x. That gives you your vertical asymptote. And then at the end, you can find your x and y intercepts. All right? And that's everything. So with that in mind, let's do some examples. So the first one we'll do is f of x equals x minus 1 divided by x squared plus x minus 2. Now, as you can see, the exponent on the bottom is bigger than the exponent on top, right? B is greater than A. Therefore, the horizontal asymptote is at y equals 0, right? Just kind of the normal case. So what we'll do next is we'll factor everything, right? So on the top, you'll have x minus 1. On the bottom, that's a simple trinomial. That'll be x plus 2, x minus 1, right? Because 2 times negative 1 is negative 2. Add them together, you get 1. And if you notice, the x minus 1 cancel, and you're left with 1 over x plus 2. So that means that there's a hole when those two things cancel, right? So you have a hole at x equals 1. So there's a hole at x equals 1. Now, what is a hole? I keep mentioning that, but I haven't really explained what it is. It's just if you have a graph, there's literally just a hole in the graph, like a little spot at a point that doesn't exist. And it's so small you can't really see it, but we will actually draw it like this just to symbolize where it is. But it's so tiny because it's just at that point exactly, you wouldn't actually really be able to see it. But we do draw the hole. Okay, that's all a hole is. So with that, what's the next step? I think we have to find the vertical asymptote, right? So you set the bottom to 0, so x plus 2. X plus 2 equals 0. Therefore, x equals negative 2. That is the location of your vertical asymptote. So I got my horizontal asymptote, I got my vertical asymptote, I got a hole. All you got to find next are the x and y intercepts, okay? And you can use this version of the function, the simplified version, to solve for your x and y intercepts. So let's say you want to solve for the x-intercepts first. You set y to 0, so 0 equals 1 over x plus 2. There's no number you can divide by, right? There's no number you can do 1 divided by to get 0, right? In fact, if you try to isolate for x here, you would get x plus 2 equals 1 over 0, which is undefined. So there is no x-intercept, right? There's no x-intercepts in this one, and that's okay, right? Because there's a horizontal asymptote at y equals 0, remember? So it would make sense that there's no x-intercepts. But let's try to find the y-intercept, right? Set x to 0, so y equals 1 over 0 plus 2, you get 1/2. So there's a y-intercept at y equals 1/2. Okay? So with all this information, we can go ahead and we can plot what we have. So draw your axes like this. So we said there is a horizontal asymptote at 0, so it's just going like this. You have you have a vertical asymptote at negative 2. Draw that there. You have a y-intercept at 1/2, like that. You have a hole at 1, put it there. You can figure out what the height of that hole is by plugging in the value of 1 into the function. So here, let me go back here. So we said the hole was at 1 because we solved for that bracket. But then if you plug 1 into this, 1 over 1 plus 2, that's equal to 1/3. That's the y value of where the hole is located, right? So that hole is at a height of 1/3. So you could label that on your graph as well if you want to be really accurate, right? So this is a point, That's a hole. So you can see based on where these are, that this part of the function is going like this. Kind of the standard curve that we're used to for these rational functions. And then you're also going to have a curve either up here or down here, most likely, right? All you have to do to figure this out, if you're not familiar with what the graph looks like, is you can plug in a test point. So I would plug in a point to the left of this asymptote because I already know what it looks like to the right. So you could plug in something like -3 for x. So you'd have 1 over -3 plus 2, and that's equal to 1 over -1, which is -1. So you're down here at a height of -1. You're below that horizontal asymptote, meaning this curve must be doing this, right? Because the alternative was up here, but we got a negative answer, right? -1. So it can't be at the top, it must be down here at the bottom. Okay? So that's what your curve looks like. And that's how you graph that. And you can do it probably a little bit nicer and neater than I've done it here, but that's the main idea. I'd also label your asymptotes. Vertical asymptote at x equals -2. Horizontal asymptote at y equals 0, just to label everything, right? Okay, and that's it. Now let's do another example. And each of these examples is going to look a little bit different, right? They're all going to have their own sort of trick to them, so it's good that you stay for each and every one. So for this one, we'll have f of x equals x over x squared plus x minus 2. So again, b is greater than a, so the exponent on the bottom is bigger than the exponent on top. And we could say, therefore, the horizontal asymptote is at y equals 0. But when we factor this, on the bottom, you get x plus 2 and x minus 1, same as last time, but nothing cancels, right? And so nothing cancels, so there's no holes. Okay, well, let's find the vertical asymptotes then. So you set the bottom to 0, and you get two answers, right? You get x equals -2 and x equals 1, right? Because if x is equal to either of those, then you're dividing by 0. So you have two vertical asymptotes, right? Well, what's that going to look like when we graph it? Well, let's start putting things together. So you have one at 1, like that, and you have one at -2. Okay, so what's happening then? Well, do we have any x-intercepts? Like if I set y to 0, is it possible to solve for x? I think it is, right? 0 equals x divided by, x squared plus x minus 2. You could use this version of it too, doesn't matter. But basically what's going to happen is you multiply both sides by this denominator to get rid of it, and you're just going to be left with 0 equals x. So there is an x-intercept here at 0, right? Now, remember, there is a horizontal asymptote. So despite there being a horizontal asymptote, you still have an x-intercept. And you might say, how's that possible? I thought we can't touch asymptotes. Well, here's a secret. You can never touch a vertical asymptote, but sometimes, in special cases, you can cross a horizontal asymptote. And that's because the horizontal asymptote is acting as a horizontal asymptote for parts of the curve, but not all of the curve. And I'll show you what I mean. If you plug in a couple test points on either side of these asymptotes just to see what's going on, if you plug in like x is 2 and then solve for it, you're going to get a positive answer, meaning this curve is up here like this. Because the other option was it was down here, right? But if you plug in a test point like 2, you'll get a positive that tells you it's up here. If you plug in a number to the left of -2, like -3, for example, you'll get a negative answer. And therefore, the curve is down here. Because again, the alternative was it could be up here, but as it turns out, it's at the bottom. So I would recommend doing test points like that. So if you're not sure what I'm doing, I'm just taking a point to the left of that asymptote, plugging it into the function, and solving for it, and seeing if it's positive or negative. Positive or negative because the horizontal asymptote is at 0, and I want to see if it's above or below that asymptote. So those two curves are good, but the inside part's interesting, right? Because we have this x-intercept here, and it's actually going through the origin, so that's your y-intercept and your x-intercept. So what's going to happen? Well, you can do a test point here between 0 and 1, and a test point here between -2 and 0, right? Just to see what's happening. If you plug in -1 into your function, you're going to get a positive answer. And if you plug in a number between 0 and 1, like a half, you're going to get a negative answer. Okay? And what that tells you is that the graph is doing something like this, where you have a curve like that, and then a curve like this. So this middle one, it's still going towards those vertical asymptotes, but it's crossing over the middle. It doesn't care about the horizontal asymptote. The ones on the outside do. They care very much, right? So the key to this is find your asymptotes, horizontal and vertical, see if you have any holes, factor, right? That's how you can find the vertical asymptotes, by factoring the bottom and solving for x. And then see if you have any x or y intercepts, and then do some test points, right? Plug in some values of x on either side of the asymptotes and on either side of that x-intercept, and you'll see where your curve is. And if you know where it is, you can just fill in the rest, okay? And you're going to see, after doing lots of these examples, there are only so many shapes that you're going to see over and over again. So far we've seen kind of two different types of shapes. The kind where you have a curve on both sides like this, and this one's kind of similar. You still have those curves on either side. You still have this and this, but you also have this weird thing in the middle. And that happens when you have two vertical asymptotes instead of one, right? Okay, so let's move on now to another example. Let's say you have f of x equals 3 over x squared plus x minus 2. So if we're thinking about the horizontal asymptote, the exponent on the bottom is still bigger than the exponent on top, right? A is less than b. Therefore, horizontal asymptote at y equals 0, right? Just like the last two. But again, just because the horizontal asymptotes are the same doesn't mean they don't look very different, right? So what do we have? Well, let's factor the bottom. You'll have 3 over x plus 2, x minus 1. Same as the last couple, right? Keep it simple. And that means we have vertical asymptotes at x equals -2 and at +1, right? And there's no holes, nothing cancels out. So if we're going to graph this, what do we have? -2, 1. So you got your asymptote there. You got an asymptote here, horizontal one at 0. We can check for x-intercepts, and if you think about it, if you do 0 equals 3 over x plus 2, x minus 1, so I set y to 0 because I'm trying to find the x-intercepts, right? If you think about it, what would you have to divide by to get 0, right? Like 3 divided by what is 0? Well, nothing, right? And if you multiply both sides by that denominator to get rid of that, you'll get 0 equals 3, which doesn't make any sense. There are no x-intercepts here, right? There's no x-intercepts. But you could find y-intercepts, right? You find y-intercepts, you set the x's to 0, 3 over, and I'll use this version of it just to keep it simple, 0 squared plus 0 minus 2, you get -3 over 2, which is -1.5, right? So you do have a y-intercept, right? It's down here at -3 over 2. So because it's down here, and there's no x-intercepts, you're never crossing the x-axis, that tells me that the curve you have is all underneath here. So it must be like this. Just like that. So instead of having the one where you cross and you go like this one doesn't have an x-intercept, so it can't cross over, so it's all on the bottom like this. Kind of looks like a quadratic, but it's a little bit different because it just gets taller and taller. It doesn't get wider and wider forever because it stops at these asymptotes, right? But it does have that sort of horseshoe shape, right? Now, you can do some other test points. Try a point to the right of 1, like 2, or to the left of -2, like -3. And they're both going to be positive if you plug in those x values into your function and solve. And because they're positive, they're both on the top like this. And so you get a curve like that and a curve like this. And that's it. That's your answer. Let's move on to another one. Let's say you have f of x equals x squared plus x minus 2 divided by x plus 2. Well, we got to recognize that the top has a bigger degree than the bottom, right? And so the horizontal asymptote must not exist, right? There must not be a horizontal asymptote, although it is bigger by exactly 1, so maybe it's a slant asymptote, right? Well, let's factor this and see what exactly is going on. Because if you factor the top, you get x plus 2 times x minus 1 divided by x plus 2. Well, the x plus 2's cancel, and you're left with x minus 1, meaning that there's a hole at x equals -2. Right? You set that bracket to 0, solve for x. But the remaining function we have left over, the x minus 1, that's just a linear function, right? It's a linear function. So what we have is a linear function with a hole. That's really what we have. It doesn't look like a curve like the other functions we've done, right? So if you go to graph this, all you're going to have is y equals x minus 1, which looks something like this, right? There's a y-intercept of -1. and there's a hole at -2. So down here at -2, say that's -2, you have a hole there. So you just label it like that, right? And you could label the x-intercept there. You could figure it out. It would be 1. You know, figure out things like that. You could figure out the y coordinate, or the y part of the coordinate for the hole. You just plug in -2. -2 minus 1 is -3, so that's at a height of -3. So you could label things like that, but for this one, it's very straightforward, right? Once those cancel, you're left with a linear function. It just so happens to have a hole in it, right? So you draw your linear function and then put a hole, and that's it. Okay, let's do another. Let's do f of x equals x squared plus x minus 2 divided by x squared minus 2. So in this case, the exponents are the same, right? A is equal to b. Therefore, the horizontal asymptote is at, well, what are the coefficients? This is a 1 and that's a 1, right? Because they're not written. So the horizontal asymptote is at y equals 1 over 1, or just 1, right? Now, if we try to factor this, on the top you have x plus 2, x minus 1, and you can't factor the bottom, right? Unfortunately. It looks like a difference of squares, but 2 is not a square, so you can't factor it. Nothing cancels, so there's no holes. Okay. You can try to find the vertical asymptotes, right? You can set x squared minus 2 to 0, and then solve for x. You get x squared equals 2, square root both sides. X equals plus or minus the square root of 2, because when you square root both sides, you gotta use the plus or minus. So that's where your vertical asymptotes are. You have 2 of them. One of them is at positive root 2, one of them is at negative root 2. So we can start sketching what we have so far, right? So you have root 2, negative root 2. Those represent your vertical asymptotes, just like that. You have a horizontal asymptote at 1, we said, so it's going to be up here. So that looks a little bit different than what we've had so far, right? And then you can try to find your x-intercepts. So x-intercepts, you set y to 0. 0 equals x plus 2, x minus 1 over x squared minus 2. And really, you multiply the other side with that denominator to get rid of it, and you're left with 0 equals x plus 2, x minus 1. This happens a lot, and so you can kind of infer that the rule you should be using is just, set the top to 0 and solve for x, and that is going to tell you what your x-intercepts are, right? So to find the vertical asymptotes, you set the bottom to 0 and solve for x. To find the roots, you set the top to 0 and solve for x, right? That should be the rule you take away from this. You solve for x in each case. X equals -2 and x equals 1. So you can put those on the graph. -2 would be over here, so that's an intercept. And then x equals 1 would be about here, so that's also an intercept, just like that. Now you can figure out if you have any y-intercepts, right? Y-intercepts, you set x to 0. So you would have y equals 2 times -1. So I'm just plugging in zeros for like these x's, right? You'd get 2 times -1. And then on the bottom, you'd get 0 minus 2, so just minus 2. And that's just going to equal 1, right? -2 over -2 is 1. So you have an x, so you have a y-intercept at 1. That's right on your horizontal asymptote, right? Same as that question we did a couple questions ago. And what's nice about this is you can kind of see a couple of the points how it's working already. So you have a curve that goes like this, and a curve that goes up like that. If you do a point over here, you'll see that it's positive, and therefore it's, or not just positive, but above 1, and therefore it's above your asymptote like that. So you have a curve going like that, curve going like that. On the left, you see you have a point here below the asymptote already, so you know the curve here is going to be going like that. And then the one over here, if you're not sure, plug in a point over here like 3, and you plug it in, you're going to get an answer bigger than 1, telling you that the curve is going to be like this on top, as opposed to being underneath like this, right? And that's it. That's your function. So that's how you graph that. I got a couple more here that are kind of unique examples. So this next one, f of x, is equal to x squared plus x minus 2 divided by x minus 2. So you can see that a is bigger than b, but it's only bigger by 1, right? So this is going to be an example where you have a slant asymptote, or an oblique asymptote, you could call it. If we factor this, you get x plus 2, x minus 1 over x minus 2. So nothing cancels, so there's no holes, right? So we have no holes, and we also have a slant asymptote. So those are the two things we know so far, right? Now what about the vertical asymptote? Well, you set the bottom to 0, solve for x, you're going to get x equals 2. So you have a vertical asymptote at x equals 2, there's no holes, and there's a slant asymptote. Now, how do we figure out where the slant asymptote is or what it looks like, right? Because a slant could go like this, but it could also be like this, it could be like this. We don't know what it looks like, right? We don't know the slope of it. So that's what we have to find. We have to find the actual equation of the slant asymptote. So it's going to be a linear function, right? It's going to be a straight line. So all you have to do is actually divide these things. And to divide them, you can use synthetic division or long division. Let's do long division here. X squared plus x minus 2, and we're dividing by x minus 2. So let's do our long division. X squared divided by x is x. X times x is x squared. X times negative 2 is negative 2x. We subtract, you get 0 plus 3x. Bring down negative 2. 3x divided by x is 3. Now at this point, this is your answer. We don't care about the remainder. I'll finish the question. 3 times x is 3x, times negative 2 is negative 6. Subtract, and you get 4 as your remainder. But again, we don't care about the remainder. We care about what's on top here, because that equation on top is going to be the equation of the slant asymptote. So y equals x plus 3. This is the equation of the slant or the oblique asymptote. Okay? So we need that as well. Now let's put all this together. I'm going to draw my plane here. So we said y equals x plus 3, so it has a y-intercept of 3 and a slope of 1. So actually I'm going to draw this with a dotted line because it is an asymptote, right? Something like that. Just like that. And then we also know that there is a horizontal asymptote, or sorry, we also know there's a vertical asymptote at 2. So I'm going to draw that here. That's at 2. Just like that. Now we can draw the graph. We're going to need to figure out some x-intercepts, right? As we discussed in the last example, we set the top to 0 and solve for x. The top of this is just x plus 2 times x minus 1. So you're going to get x equals negative 2 and positive 1 for your x-intercepts. So negative 2, you have to figure out where that is. Is it to the left of that asymptote or is it to the right of that asymptote? That's important, right? Well, I'm going to show you negative 2 is actually here and 1 is actually here. And the reason I know 1 is there and negative 2 is here, and negative 2 is not over here, for example, is because you can figure out where this asymptote crosses the x-axis. So you should absolutely do that. So again, this is y equals x plus 3. So you set x to 0. So you set y to 0 to find the x-intercept. Bring 3 to the other side, you get x equals negative 3. So negative 3 is where that is. So that means that negative 2 is to the right of it. So you absolutely have to figure that out. Otherwise, you'll have, oh, there's a point over here. It's like, how do you connect these dots together, right? So we know it's on the inside here because of that. Now, what's going to happen on the bottom here is these are going to connect like this. And you have a curve that kind of does something like that, if you can imagine it getting closer and closer to those asymptotes. So that's what's going on the bottom. And then on the top, there's a couple things that could be happening here, right? You could have a curve here, or you could have a curve here, fitting between those asymptotes there. It's actually going to be this one here. And the way you figure that out is by determining the height of the function, this curve here, at a point just to the right of 2. So take like 2.1, for example. Figure out the height of the function and compare it to the height of the linear asymptote here, the slant asymptote, and see which one's taller. If you do y equals 2.1 plus 3, so I'm just using the equation of the asymptote, the y value of that is going to be at 5.1. But if you do the original function and figure out the height at 2.1, you're going to have y equals 2.1 plus 2 times 2.1 minus 1 divided by 2.1 minus 2. If you calculate that, you're going to get 45.1. That's much, much taller than 5.1, meaning that the function is way up here, because it is very, very steep at that point. So it's very high up, much higher than this point is at that same height. So that tells you your graph is up here and not down here, right? That's how you figure that out. So this is your final answer, okay? So get used to seeing a slant asymptote and a vertical asymptote with two curves wedged in between them, just like that, okay? We're going to do one more example here. Last one, y equals 6 divided by x squared plus 4. So the exponent on the bottom is greater than the one on the top, so a is less than b. So therefore, we have a horizontal asymptote at y equals 0, right? We can ask ourselves, is there a vertical asymptote? Well, no, because you can't solve for x on the bottom, right? If you do x squared plus 4 equals 0, x squared equals -4, square root both sides, x equals square root -4, can't do that. It's not a real answer. So we don't have any real vertical asymptotes here. So there's no vertical asymptote. We could figure out the y-intercepts, right? Set x to 0, y equals 6 over 0 plus 4. That's the same as 3 over 2. So y equals 3 over 2 is a y-intercept. You could try to find the x-intercepts. But to find the x-intercepts, we said you just set the top to 0. Well, there's nothing to do here. 0 doesn't equal 6, so there's no x-intercepts either. All you have is a y-intercept to go off of here, and also your horizontal asymptote. So this is a very special case, and you're going to come across this most likely, so it's good that you see it first. So if you have a horizontal asymptote at 0, I'm going to draw it just like this so you can see it. Horizontal asymptote at y equals 0. The y-intercept is 3 over 2. I'll put that right here, 3 over 2. This curve is going to look just like this. It's going to come down like this, and then kind of swoop and get close, and then over here, it's going to do the same thing. So it kind of looks like a little hill, right? This should be a smooth transition, and then it gets to the top, and then it starts going down, just like that. That's all it looks like, right? That's all there is to this one. So some people see this and they get confused because, how could you have no vertical asymptotes? How could you have no x-intercepts? All these different things. And this is really all there is to it. It goes up and comes back down. Just a nice little hill. Okay, and that's it. So that's, for the most part, every type of rational function that you'll come across this year that you have to graph. So if you're comfortable and familiar with all of these techniques, you should be confident in your ability to graph these functions.